Hello, everybody. We are representing the University of Southern California. My name is Seismic, and the team members are Ravi and Maria Muhammad. And we would also like to take this opportunity to thank the EERI and the Student Leadership Council for organizing this event. We are very excited to be here and to see the results of all our hard work. So, during our design, we focused on a few main points. We wanted to make sure we maximize the floor space, so we would have optimal revenue, while we were also trying to minimize the weight of our structure and therefore minimize construction costs. Also, during seismic design, we were considering wanting to ensure that we have even load distributions, therefore minimizing structural damage. And also, we wanted to minimize any repair costs if any should arise. Now, as you can see here, for our floor plan, we utilized the cross-diamond configuration. Our dimensions were 13 by 13 and 60 inches. This gives us 29 floors. And then along our height, we had continuous columns, which we concentrated in the edges of our permanent floor plan. We anticipated higher moisture stress at the corners, therefore we increased the number of columns there. We also placed shear walls 12 inches from the base of our floor plan, where we anticipated higher shear forces. Bracing within our structure, we placed from top to bottom to minimize deflection. And now Rafi will discuss the construction process.
Thank you, Alex. Well, this phase of the project is where someone has to be very precise. So some of the problems that we encountered during the construction phase was just the common to the manufacturing imperfections. So that gave us a hard time with the measurements, to make very precise measurements. Another problem that we encountered was the density variation in wall solid. So our building is not uniformly constructed, so we're expecting some weak points and some strong points. Also, another problem that we encountered was the glue was taking so long to dry, and so we ended up building phases with a few floors and we start from the bottom and go back. But sometimes the problems might arise from places that we least expected. So my team and I kind of instead of focusing on building the structure. So as you can see on the right hand, sorry, our team is taking some West Coast moves. And that's me dancing to the structure and not the smoke. Of course, safety is a big issue, but generating income is important as well. So after calculating our floor area, we generate annual income $714,000. Subtracting that from the total cost will become $414,000. Maria to talk about analysis.
We used SAP 2000 to model our structure, and the two assumptions that SAP usually makes that are not true for our case was, the first one is SAP assumes that all the members have the same material property, which is not the case for balsa wood since each member is cut from different parts of the tree. Also, SAP assumes that failure will not happen at the different connections in the building, which is also not true in this case. So in order to get precise predictions, even though we're using SAP with these strong assumptions, we performed our own experiment using a shape table for El Centro and Northridge, and when we did this experiment, we applied a point load at the top of the structure. And in addition to this, we also tried to find the natural frequency of the building as a whole, and we went through different trial and error process of modifying the modulus of elasticity of our structure until the final natural frequency was the same as the one we got from our free vibration test. Based on that, we were able to make a prediction using a time history analysis for El Centro, our drift to be about 1/4 inch with an acceleration of 0.9 g, and for Northridge with a drift of about 1/2 inch with an acceleration of 1.6. Thank you, and do you guys have any questions?
I didn't catch the lateral system. Can you back to the picture you modeled and just describe your lateral system?
We have two lateral systems. The first one is the shear walls at the bottom. They will catch the base shear that will go down. That is being transferred as a result of the bracings, and the bracings will transfer each floor shear to the edge columns, which inevitably take it down to the shear walls.
How do you connect your bracing to the top of the shear walls?
There is a connection at the edge where there is a corner column that the bracing is attached to, and the shear wall is also attached to the corner column.
In your analysis, if you remember, how much is the percentage of the base shear that's taken by the shear wall and compared to the columns?
We didn't really have those numbers when we did the analysis. The analysis we basically focused on the roof deflection, and that was the forces that were going.
Curious in the picture, did you add weights to that tester?
We applied a point load at the top.
So you use that to calibrate your model for the fundamental period, correct?
The fundamental period was done without the plate on it. So it was just an actual period.
It's based off of mass. In this case, you don't have any mass. You just have the mass of the structure. Do you think there's some inaccuracies in that?
There will probably be some inaccuracies in terms of converting the amount of mass we applied versus the amount of mass that will be applied tomorrow. But when we calculated the natural frequency, we were modeling the structure without having a point load on it. The purpose of the natural frequency was just to minimize the error that will be caused as a result of different material properties for each member.
Any further questions?
Do you have an estimate of that?
Oh, it was about 7 minutes.
7 minutes?
Mm-hmm.
Okay, thank you very much. Another round of applause.